when the source gets closer, the wavelength seems shorter, and when the source and the receiver are moving apart from each other, the wavelength seems to be stretched. This is called Doppler effect, and it is the cause of the characteristic sound of a passing fire siren. In this video, we want to learn how neutral atoms can be cooled by means of laser light. This seems very counterintuitive, as things usually get warmer by shining light on them. Actually, the key will be the Doppler effect. Assume we have a single neutral atom. The core is basically an attractive Coulomb potential where electrons are bound at specific energy levels. An external photon that carries the right amount of energy can trigger an optical transition. This means that the photon is absorbed and the atom gets excited to a higher energy. After a while, the atom will relax into the ground state by spontaneously emitting a photon of the same energy as it previously absorbed. Now imagine we have a setup where the laser is slightly detuned to the red of the optical transition. In other words, the photon energy is slightly too low to excite a resting atom. An atom moving in the same direction as the photon could neither be excited. Due to the Doppler effect, the wavelength would seem to be stretched and the photon frequency would therefore be even further away from the resonance frequency of the atom. On the other hand, when the atom and the photon move in opposite directions to each other, the photon may hit the resonance. The energy gets absorbed and so does the momentum of the photon. As a result, the atom is slowed down, or in other words, the atom is cooled. After a while, spontaneous relaxation takes place. The emitted photon again carries energy and momentum. However, the direction of the recoil momentum is completely random. Therefore, after many such spontaneous emissions, there is no average momentum gained. This technique of cooling neutral atoms is heavily used to reach very low temperatures around 10 microkelvin. Of course, there are some limitations that need to be considered. For example, concerning the density of a cold atom gas, it is important that atoms don't scatter with each other while they are excited. Otherwise, the excitation energy could be transferred to kinetic energy, which would result in unwanted heating. The limiting factor for the temperature is actually the natural lifetime of the excited state and not the photon momentum, as one could think. Let's figure this out. Once the atom is completely still, it will randomly gain momentum due to the absorption and emission process. You may imagine this as a random walk in momentum space around the origin. If the lifetime is short, photons will scatter quite often with the atom. Each time a photon momentum is transferred. In this case, the random walk in momentum space often gets carried away from the origin by many photon momenta. Although the mean momentum still averages to zero, the mean of the square momentum, which actually enters the kinetic energy, is large. The lowest temperature we can reach is called Doppler temperature or Doppler limit. Under certain conditions, the Doppler temperature can be motivated by a back-of-the-envelope calculation. Let's consider the power transfer between the laser and the neutral atom gas. The heating power is proportional to one photon's energy per lifetime, where we omit normalization and multiplication by the intensity. The cooling power is loosely speaking the rate of loss of momentum in a distance per time. With this quick argument, we indeed see how the velocity squared relates to the lifetime of the excited state. And we even find the correct expression for the Doppler temperature. That's pretty much it. Thanks for watching.